Yeah, we're just gonna wait for the whole team to be ready and we can begin.
Okay, that works for us. Like I said, we're ready when you are.
Okay.
All right.
Our friend Telma is having a little bit of trouble with the meeting, so we're just trying to figure out what's going on.
Oh, that's fine.
Okay. Okay, I think we're all ready, so I'm gonna go ahead and share my screen.
Okay, we'll hold all our questions till the very end, so we can get started.
Okay. Hello, good afternoon to everyone present at this meeting. We are Team 1086, Mrs. Atafi, and we will be presenting our preliminary design review. The presenters of this document are Natalie Buenavides, Paulina Duarte, Guillermo Alejandro, Alan González, Isaac Valencia, Emiliano Martínez, Telma Manuel, David Farfán, and myself, Brandon Mesa. We will start the presentation with the systems overview. The main objectives of the project are to design a Cansat capable of simulating the landing sequence of a planetary probe, implementing the specified descent control systems. The Cansat will be deployed near apogee, and throughout its descent, it'll have to fulfill different objectives shown in this slide. As an additional feature, the team will attempt the bonus objective. The first Cansat design is composed of a lightweight container that includes a small PCB for basic components and a probe that occupies most of the space. And it also contains the release systems and the flight electronics. The second design changes the probe parachute release system and the error brake, which is reflected in a size reduction in both of the probe and the container. The selected configuration will be the first one presented since it better meets the requirements of the competition. Discussing the physical layout in more detail, a general image of the chosen design can be seen. The parachute release system and the heat shield, the PCB to be used, and the energy storage space. The approximate dimensions of the container and the probe are kept within the dimensional limits established by the competition. Here is shown in detail the organization of the probe's electronic components and their placement both on the PCB and on the structure itself. The heat shield opening mechanism implements a system that transforms the rotary motion of a servo motor into the linear motion of a slider. As for the mechanisms required for the release of the parachute and the raising of a flag, we decided to place them in the same unit with a detachable top cover. Once the top lid has been released, the flag raising mechanism can move freely and perform its function. Following the system concept of operations, the sequence of events starts with the launch, followed by the Cansat deployment, probe release and heat shield opening, probe parachute deployment, and ending with the probe landing and uprighting. Here are shown in more detail the activities to be performed during the mission and their classification in different stages: pre-launch, launch, and recovery. Finally, the dimensions of our Cansat are 382 millimeters high and 116 millimeters in diameter, which leaves enough free space inside the payload bay of the rocket to ensure the correct deployment of the prototype.
Hi, I am Natalie, and I'm going to present to you the sensor subsystem design. Next. We have the different proposal of sensor to be used for both the payload and for the container. Sensors are divided like to weather work under different variables that can be checked. The sensor proposals for the payload are the barometric sensor that will measure air pressure, a temperature sensor, a voltage divider that will measure the Cansat battery level, a gyroscope that will help use Measure the tail angles of the payload. A GPS do not work is the payload. A servo motor system that gets the relay system. A switch to turn and off the Cansat. The container will have a video camera that will record the flight from launch to landing. Next. The sensor chosen for the measurements of air pressure is the BNE 280. Since it has a communication interface, I2C and SPI allows use a duplex communication between an AVR device and peripheral device or between some microcontrollers. Next, the temperature sensor chosen for the payload is the DHT22 because of its measuring range and grid precision. Next, we choose a voltage divider made up of two resistors, one of 30 kilo ohms, another of 7.5 kilo ohms, because it's easier to put in the PCB, smaller and lighter. Next, to measure payload lead angles, we choose the gyroscope GY521 to the motion detection is in 10 axis. The communication call to it both bus, SPI, and I2C, so it's easy to get the measured data. Next, the GPS is ideal to be controlled with any microcontroller and includes a ceramic antenna ready to be installed on the PCB. Next, finally, the camera that will record the prompts, flying signs, launch, until landing will be SP32 cam. Due to the high video resolution, it has also because it has an integrated SD reader module and accessories.
Hello, my name is Paulina and I will talk to you about edison control design. Next, please. This image shows the Cansat schematic with each of its modules. Gray structure, thermal protection system and video recording, yellow module, battery sound, red module, electronics, sensors area, green module, release system, purple module, compartment and parachute deployment system. Next. The purple release system operates with a pistol system controlled by a thermal module in the center. Its components are shown in the table. Next. The following diagram shows that the Cansat will be released near apogee. It will descend at 50 meters per second, and at 500 meters, it will release a probe which will deploy a heat shield and fall at 20 meters per second. Finally, it will deploy a parachute at 200 meters and descend at 5 meters per second. Upon landing, it will straighten up and deploy a flag. Next. The three fundamental parts of the mission are descent of container, descent of the probe, safe landing, and post-landing requirements. Next. The image shows the first option of the probe parachute deployment system. The container parachute won't have a release system, while the probe will have a servo deployable module. Next. In configuration 2, the container parachute will be the same as the previous one. However, the deployment system of the probe will be a servo-operated lead. When opened, it will let out the parachute. Next. For the air brake, there are three different proposals. The first consists of an inverted umbrella mechanism with ceramic blanket fabric. Its advantages are its large contact surface, its speed of 20 meters per second, and its resistance to high temperatures. Next. Configuration 2 is the same inverted umbrella system but with aluminized fabric. Its advantages are its large contact surface, easy deployment, high temperature resistance, and low cost. Next. Configuration 3 is a device designed by the team that functions as a heat shield and air brake. However, it has not been tested yet. Its advantages are its low weight and the small size. Next. The configuration selected was number 2 because it has lighter material, is low cost, and resistant. Currently, there are no 3D designs for a mechanism to stabilize the probe during air braking. However, the team is currently working on proposals and will have a design ready for presentation at the CDA. Next, there are two parachute design options. Design A is a flat hexagonal parachute and design B is a hemispherical one. They were chosen for their strength and commonality. Next. Design A, the flat hexagonal parachute, is made of Bristol fabric. It was chosen because it is easy to manufacture, guarantees deployment, and is durable. Its main disadvantages is that it has no steel hole. Next. Design B, the hemispherical parachute, is made of Bristol fabric. It was chosen for its strength, small, and lightweight. Its main disadvantage is complicated manufacture. Next. Design C was selected because of its properties mentioned above. Next. The following constants and formulas were used to calculate the descent of the parachute and the air brake. Next, in this section, calculations were performed for the flat hexagonal parachute with a speed of 5 meters per second. In each case, the required speed size of 5 meters per second, the drag coefficient depending on the type of parachute, 0.75 or 0.8, and the mass, 500 or 700 grams, were taken into account. The formula of the contact surface area in the air direction AC takes into consideration the three previous values, so it is regardless of the type parachute. Next, flat hexagonal parachute at 5 meters per second. Next, hemispherical parachute at 5 meters per second. Next, hemispherical parachute at 5 meters per second. Next, air brake and an estimated drop of 20 meters per second.
Hello, I am Guillermo Alejandro, and I will present the mechanical subsystem design section. We can observe below the overview of the indispensable subsystem of the Cansat. The first one is the parachute deployment system, of this case the proof, the structure of the payload, the flight computer, and finally the payload housing. Next, the configuration were mainly focused on the proof. They were integrated for various modules. One of these highlights is the air brake, that also functions as a deployment thermal shield. Another highlight is the parachute system that will be separate from the rest of the proof. The actual measurements of the proof are 98.994 millimeters times 362 millimeters. Next. Additionally, in the following configuration, the areas that make the difference are the recording system that is inside the casing. The air brake has a completely different design and a passive system, and the parachute system, which in this case is of the hatch type. Next. The important areas are the ones that will block the proof with the casing, which will only be some holes where the piston type system can be held. The camera area that is on the bottom, where it has no space. Next. The design feature openings of the top to allow the parachute course to enter, as shown in the illustration, so that when it is expelled for the rocket, it will deploy. Next. As we can observe, the system is fully active, since servo motors are required for the all deployment mechanics, the parachute, the flag, and the thermal shield system, for which a lever crank mechanism was used. Next. Similarly, the deployment area of the parachute and the flag is activated with servo motors. Only the thermal sheet area and the wind tunnel shock absorber system is passive, so it cannot be controlled. Next. The proof deployment area is a rotary to linear mechanism with the sliding crack arm system on both sides, similar to the movement of a piston. Next. Which will be removed from the casing, causing it to be released itself. Next. The mechanism will be deployed with more servos, which serve as anchors. This will move to a determined position to release the last module, expelling it and deploying the parachute. Next. On landing, the same system was used for the thermal ship will write the proof as shown in the slide. Next. What is shown below in the mass table is the mass table of the flight computer. In the same way, we obtained a SIF 400 scale, which gave us the measurements. Next. In the structural part, printed in ABS-CF, at 30% fill was considered. The screw and nuts are made of steel. Next. Given the previous data, we obtained a total mass of 688.24 grams with difference of 11.75 grams to the limit established in the competition, in addition to including some proposal for reducing the mass further. Next.
Hi, I am Alan. I'm going to present the communication and data handling subsystem. Next. Here, we'll illustrate how the communication of the proof electronics with the microcontroller will be achieved using some serial communication protocols. Next. For the payload processor and memory, we considered two options, an ESP32 and a Raspberry Pi Zero. The final decision was to use an ESP32 because it consumes less current, is smaller and lighter, has a larger number of interfaces, and also its architecture allows it to handle multiple tasks. Next. For the proof antenna, we have two options, to use the PCB antenna that comes integrated in the XB Series 3, or to use a monopole antenna that will be connected to XB Series 2C. In the end, we opted for the first option for several reasons. The most important is because we will save space and weight, keeping the same gain as the other antennas. Next. Here, you will find the prof antenna integrated in the XB, and this, in turn, is part of the prof electronics contained in the next section. Next. Regarding the prof radio, our final selection was the XB03 Pro, as it has the best transmit power, receive sensitive, and line of sight range of any XB operating at 2.4 GHz. Regarding the transmission control, we identified three main moments of the mission. Before the launch, the ground station XB will transmit the corresponding commands for telemetry, calibration, and timing. During flight, the Prof XB will transmit telemetry to the GCS, and after landing, the ground station XB will send the command to turn off telemetry. Next. Here is a bit of the XB configuration. Complying with the requirements of the competition, the network identifier is our team number, and the XB doesn't operate in broadcast mode, as seen in this screenshot with the destination address high and low. Next. The telemetry file, description, and examples of the data to be contained in the telemetry package. Next. The complete telemetry package and example using hypothetical data. Next. And finally, the commands to be sent to the prof with format, description, and some examples using our data.
Hello everyone, I'm Isaac Valencia and I'm going to present the electrical power subsystem design. Next, please. Here we have a table with the elements of the payload and container that will provide, regulate, and make use of electrical energy. Next. This is the relationship between the different batteries of the probe and container with the elements that will require their energy. Next. This diagram shows the exact energy consumption for each element of the payload. And there is an external switch to measure the voltage without disassembling the Cansat, and umbilical power source to power the entire circuit without using the batteries. Next. Here we present the different options of batteries that we consider, emphasizing that all are rechargeable batteries. Next. For the energy source that will power the payload components, the rechargeable Lion battery 18650 was selected for its greater capacity, size, and cost. We will use two batteries in series to increase voltage. And for the real-time clock, we have a coin battery. Next. Finally, this table shows the power consumption in watts per hour for each element and in total. The available power is enough to power the system for more than 2 hours. Thank you.
Hi, my name is Emiliano, and I'm going to present you the flights of design. Next. The information that it will give the operation to the Cansat will be routed as shown in the flow diagram, considering the simulation mode to activate or deactivate the pressure sensor, the connection with GCS, and the data packaging for sending. Next. C++ language will be used to program the flight computer due to the choice of hardware and the knowledge and the familiarity of its use. Next. Two development environments were chosen, Arduino EDA and Visual Studio Code. Like the choice of the language, this decision was made due to familiarity of their use and tools they possess, such as extensions that facilitate the work. Next. The list of flight computer tasks is so long and can be divided into 4 axes: automatic control, telemetry, simulation mode, and redundancy. Next. The payload will go through different states. This will be delimited by the height at which it is located, triggering certain mechanisms according to these criteria as shown in the diagram. Next. Here we have the sampling range of the sensor. Next. The simulation mode will help us to ground testing. To activate, 2 commands will be needed to the first one to enable it, and the second one will activate it. Only one is needed to disable and deactivate it. Next. The development of the flight computer will be divided strategically and according for the resources we already have in 4 phases. In order, these are individual code per sensor, automation, redundancy, and simulation mode, integration and cleanup, and long-range testing and telemetry sending. Next. And finally, we have the members of the development team. Thank you.
Hello, my name is Delmar, and I am going to present the part of the ground station. Next, It is an interface that it communicates with an HB radio that will be connected to the Yagi antenna with the tracking system. Next, the ground station will have a laptop, an antenna, tabs, and chairs. To prevent mishaps, we have a fan with portable batteries, window automatic will be deactivated, and additional laptop if necessary. Next, 3 antennas are proposed. The commercial Yagi antenna, a helical antenna, and proprietary design. We compare the advantage and disadvantage. Next, radiation parents of the antennas are shown for the choice. Next, we chose OO design because of the low manufacturing cost. It's high gain, it's a directional antenna, it's low interference level, and it's easy to use. Next, this is the antenna mount. Next, due to expert gain from past competition, the Visual Studio ED will be used. Here is the initial screen showing the team logo and selection buttons. Next, we are looking for two main things: that it is easy to understand and that its the use is intuitive, and it will be used in untouched events. Next, where we see the prototypes of the interface, what it's divided into 5 sections: the initial section and the special section for sensor, command activation, real-time graphics, and the camera time its complement for the decimation events. Next, we used Visual Studio for the programming of the interface, HCTU for the HB modules, and Canva graphic design to be used. Next, the LiveShapes library was used for the creation of the real-time graphs. Next, for the activation of the commands, we will dedicate a page. The page will consist of buttons that activate the necessary commands. In order to have a backup copy of the received data, a CSV file will be created. Next, a micro SD will be used to have a backup of the information that will later be converted into a PDF file. For the graphs, Windows 4 will be used and converted into JPG files and transferred to use CB for presentation. Next, when the information arrives to the interface, and the same time a copy will be made in a CSV file. Next, when this mode is activated, a line of data will be read from a CSV file, which will be sent to the container and set and sensor data. It is also purports to display the graphs on a website. This for scientific measurements purpose.
Hello, I'm David, and I will tell you about the integration and test. Next. The overall objective of this section was to collaboratively devise a procedure to ensure that all subsystems will work. For this, we first decided to separate the different systems and devise a testing methodology according to the requirements of each one. Next, once each subsystem was analyzed, we proceed to couple them for an integrated system test, an environmental test, and a simulation test. Next. Now, I'm going to tell you about the requirements compliance. Next, in this section, we show the progress of compliance in accordance with the requirements of each of the different systems. Next, with the previous analysis, we can identify 9 aspects to improve. This is due to different factors such as the lack of physical tests on certain materials. The preliminary design of the Cansat is still undergoing test. Now, we will focus on the physical test for the CDR with intention to purchasing the material in the next few days. Now, my partner Brandon.
And finally, we will discuss the team management. To keep track of the activities carried out in this first stage, we use a tool called Team Gantt, which allows us to generate activity calendars, Gantt charts, and task lists with the same database. In the following 7 slides, all the activities to be performed throughout the competition are shown in table format. This first slide shows the activities to be performed by the management team. At the end of the first slide and up to the beginning of the 4th slide, the most important general activities of the team are listed. From the 4th slide to the 6th slide, the summary activities of each work area, ground station, the mechanical design, flight electronics, flight computer, and telecom are listed. The summary was limited to 6 activities per area. The last slide presents the vacations considered by the team. As for the team's conclusions, we divided them by area, and in each area by major accomplishments and unfinished work. In the administration area, we managed to organize the team to optimize the workflow. We organized a successful recruitment, and however, we still don't have any sponsors, and the procedures for traveling abroad are not yet complete. In the mechanical design, the theoretical weight of the prototype was kept below 700 grams, and most of the mechanisms to be used were thoroughly considered. Despite all this, the team still does not have a reliable design for stability control, and the integrity of the heat shield deployment structure is not yet proven. For the electronic design, the sensors and microcontrollers were selected based on previous experiences of the team, and the material selection and corroboration tests are still pending. In the case of the software, simple designs were achieved with a high level of adaptability and can be easily integrated with the designs of other areas. However, more exhaustive testing is required. For the communication system, smaller and lighter antennas were chosen, and some progress was made in the design of the ground station antenna. But the tests to corroborate the correct performance of the antennas have not yet been performed. And finally, why are we ready for the next stage? Well, the preliminary design chosen was thoroughly concept tested, and we believe it's ready to begin the next stage. At this time, almost all the milestones have been achieved and our schedules have been completed on time. Our design meets the requirements established by the mission guideline, and the team is motivated to start the concept testing with the physical development. Thank you. That would be all.
That was a very good presentation. Can I have you go back to slide number 29 for me, please?
29, sure.
Um, 29, 29.
Yeah, I'm just trying to, yeah, okay. 29. Okay.
Oops. Whoa. Okay, there. Oh. What? Oh, I'm sorry. Slide 39. Come down about 10 slides.
Okay.
Well, actually, stop right there. That is done excellent. Okay. You indicated on the slide what was selected, and you showed the options, and you did the trade correctly. Now let's go to slide 39.
39. Okay.
Okay, go back up one. That's configuration 1. Go to the next slide. That's configuration 2. Which configuration was selected?
The configuration number 1.
How do you know that? How do I, as a judge, know that?
Yeah, I see the problem.
Okay, that's the problem with several of the trades, is that the selection and trade was done very nice. The trade was done very nicely. The selection was left off. So I don't know if that means a missing slide or whatever, but anyway. Also, please go to page 49 for me.
49, yeah.
Okay. Go down, go. Okay, what part of the, okay, this says flat hexagonal parachute at 15 meters per second, but what is it attached to? What is it for? Is it for the container, the payload?
Well, I think that we did all these different slides to indicate the different options that we considered. In the slides before, we actually showed what kind of parachutes we would choose.
no. That area, that particular part really needs to have a table that summarizes the descent rates for each of the parts, the container, the payload, and so on and so forth.
Okay.
Okay, that's my major complaint, I guess, or what I basically found was that in several cases, you did the trades and didn't indicate what was picked and so on and so forth. So, and I think that was, and yeah, so. Other than that, I thought you did a really good job. Let me see here. Where's the other judge?
I'm here. Hey.
Okay, Colin.
So I agree with Ben. I think it was a good presentation. I have two questions. My first is on your ground station antenna. Slides 117 and 118. Really 118 is my biggest question. With your mounting setup. Is that a custom mount?
Yeah, actually, my friend Isaac maybe can explain a little bit better the design of the mount antenna that we are trying to display here.
That'd be great.
Yeah, we propose to use auto tracking system for the antenna of ground station, and this structure was designed consider the dimension of one of our custom antenna, and also the elements or the materials of this structure is according to commercial materials. So the idea of a ground control station is to use the GPS coordinates of both ground control and Cansat to follow the concept. But it's our own design.
Okay. Yeah, that's really interesting. So I guess word of caution. I've developed tracking systems for satellite ground stations before, and it's like the satellites that are orbiting the Earth move very, very quickly, and it's a challenge to get the controls dialed in correctly so that your ground station antenna truly follows the target. And that was with a satellite orbiting the Earth, but with these Cansats having been to launches as well, they go up, they tumble, they are unpredictable. So I guess word of advice and word of caution would be to, if you're going to go with this option, put a lot of effort into that control system. And then is that metal all surrounding the antenna, or is it just all gray?
Oh.
I'm looking at all the dipoles that make up the front of the Yagi antenna, and it's covered in a gray box. Is that a metal box or a plastic box, or?
Oh yeah, it's we consider to use aluminum tubes to fabricate this is the structure. Yeah.
Okay. Yeah. I guess yeah. Yeah. No, it's interesting. It's an interesting. I haven't seen this level of technical detail in the ground station before, so it's just interesting. I hope it works for you.
Thank you.
The other question I have, or what was that?
Yeah, that actually we have a doubt that it will be possible to implement this idea, but I think it is possible.
Yeah, no, good. I'm impressed with it. My other question is on your uprighting mechanism. So I think if I understand correctly, you're going to use your heat shield basically as to upright your payload once it lands. Is that correct?
Yeah, The idea is to retract the mechanism once it has landed, and reopen it to upright the Cansat, the probe. Sorry.
Okay, so once it's landed, you'll retract it. And does that mean that it will then fall over again, or oh no, not necessarily, no, it'll land on its side with the heat shield open. You'll retract the heat shield and then open it again to prop it up?
Yeah.
Okay, I understand. Okay, yeah, that was all my questions, so I have nothing else. Good job, guys.
Thank you.
It's been a long day. I will echo Colin's comments, and I would just, one of the things I kind of noticed, I thought the design was a little complicated. Maybe you can review a few things and make it simpler, just as a general comment. I don't know what Colin's thoughts were, but like the tracking here is, if you pull it off, that's gonna be great.
Yeah, no, if you can pull off the tracking, it would be very fun to watch at launch day. But I know that I think you guys aren't based in the U.S. Is that correct? And even for teams that are based in the U.S., the traveling across the country, even a lot of things tend to break in travel. So I don't want, yeah. I'm interested in this design, and I'm really excited about it if you guys can get it to work, but I don't want you to be disappointed if it breaks. So just be very careful and put a lot of work into it.
Yeah, we'll try.
Yeah. And wind up costing you points.
Right.
So, anyway, again, an excellent presentation. It was done on time, and we appreciate that. Do you have any questions for Colin or myself?
Well, personally, no, I don't think I have any questions.
Okay,
I don't know if my teammates have anyone.
All right. Very nicely done, and looking forward to your CDR.
Yeah.
Thank you.
All right.
Thank you.
Have a good one.
Thank you.
Thank you. See you.
Thank you.
Thank you.
Bye.